In this lesson, we're going to be looking at two very short derivations. I have both derivations on a single page of notes, so there's one derivation on the top half and one on the bottom half. And on the top half of the page, I have the derivation that we can use to calculate the force exerted on the rocket by the fuel to make the rocket go forward. Well, as I said, all of our derivations are going to start with our conservation of momentum memorized equation for rockets, negative dmu equals mdv, and this is the easiest derivation, I think, in physics ever, because the derivation is done once we divide both the left and the right-hand side by dt. And that's it. Boom. You are done. Why are we done? Well, we are done because U is the speed of the fuel. That's constant. The speed of the fuel with respect to the recoiling rocket. So combustion is happening the same way, regardless of whether the rocket is just starting to move or is moving very fast. So it combusts the same way. It goes out the back with the same speed relative to the rocket. The dm dt is going to be the kilograms, mass in kilograms, t in seconds, the kilograms of fuel being used. So please make sure you get that notation into your notes. You need to know that dm dt is the kilograms per second of fuel being used. And look what dividing by dt did on the other side of the equality. dv dt, we recognize that right away as acceleration. So mass times acceleration is force, and there you have it. Our derivation was done as soon as we divided by dt. Now, rocket scientists use the word thrust to refer to the force on the rocket. So typically, as I have here, we want the thrust, the force, to be big because we want rockets to go fast. We don't want them to just go up and then come back down. We want them to go up and keep going. And let's take a look at our equation here and what it takes to make a rocket go fast, to have a large force. So if we want F to be big, we need U to be big, right? So we need the speed of the fuel. We need that combustion to throw fuel pellets, fuel particles, molecules, out the back very quickly. We also need to have a combustion process that is going to have a large kilograms per second. So not only do we have to eject the fuel out the back fast, we have to eject a lot of it per second out the back fast. And that's why when you see rockets starting at rest on the launch pad, that they quickly drop off those initial stages, because those initial stages of the rocket have the kilograms per second of fuel being thrown out the back enormously fast at an enormously high rate of kilograms per second. So now you, I think, have a better understanding of why it is rockets look the way they do and what happens with those stages. All right. Well, what if we want to actually calculate the speed of the rocket as it's going along? Well, that's also a very easy derivation. We again start off with our conservation of momentum statement. Negative dmu equals mdv. Now we are going to just isolate the dv. So we're going to bring the m down underneath the dm. So now we get negative dm over m times u. U is a constant, equals dv. As you can see here, we integrate both sides. Constants come out of integrals, so that u is going to come out. So that's why the u is sitting out here. The integral of 1 on m dm is natural log of m. We are evaluating it from final minus initial. The integral of dv is v, final minus initial. So really, we are done here. That's it. We're done. So I have my expression for v final. All I've done at the bottom portion here is kind of rearranged it algebraically, or with my natural log of A minus natural log of B equals natural log of A on B. But the form that you use doesn't matter. You can absolutely leave it in that blue starred form that I have here and just use it if you'd like. But as you can see, the derivation for the speed of the rocket is very easy. Both of these derivations will be fair game for the AP test or for any of our quiz or tests. I won't spring it on you, but if I tell you need to know the derivations for the thrust or force of a rocket, or the derivation to calculate the speed of the rocket as it's using up its fuel, you would need to go through the derivations that are shown on this page. Now, your homework is going to be to do the example problem on the next page of notes. So, as well as I think a couple in our homework packet. But pause the video here, and then I will show you the solution, and we will talk more about the solution in class as well. But pause here and give it a try. Okay, let me show you the solution. So, if you're not asked to do the derivations, you're simply going to use the equations that were given, and we were told the rate at which fuel was being used in this problem. We were given the force, the thrust on the rocket, so we simply had to calculate the speed that the fuel was being injected, the U value with respect to the rocket. Burn time is the time it takes to use all of the fuel. And here we were told that the mass of the rocket was mostly fuel. It was 73% fuel and 27% the other stuff, which is called the payload. The other stuff is the payload of the rocket. So the mass of the fuel is gotten by taking whatever is not the payload, and that is what we've done here. And then the burn time to use all of the fuel is given by the number of kilograms per second we are using, multiplied by all of the fuel. 1 on the kilograms per second gives us the amount of time. And then finally, we are just plugging into our derived equation for the final speed of the rocket. I'm not going to go through that with you here. The final mass of the rocket is, however, just the payload. So you do have to make sure that you're using the right equation. So make sure that you get just the mass of the payload for M final. Okay, and we can talk more about this in class if you have other questions on this example or the rocket examples from our homework.